Without further ado, I would like to present the first speaker of the conference, Bladh, who will be speaking about the dusty winds of AGB stars. Go ahead, Sarah.
Do you hear me?
Yes, we can hear you.
Okay, so thank you for inviting me to give a presentation here today. I am currently working at Uppsala in an ERC project called X-Wings, which you see from the logos on top here, and led by PI Susanne Höfner. And the X-Wings team members you can see in the bottom here. So the topic of my talk today is Dusty Winds of AGB Stars. It's a quite generic title. I will talk about the mass loss mechanism in AGB stars, introduce the Darwin wind models and talk a little bit about them, and hopefully share some recent scientific results. This is an artist's impression of sort of the life cycle of a low to intermediate mass star, from birth in the molecular cloud to its death as an AGB star. So AGB stars represent the late stages of evolution for low to intermediate mass stars. They are characterized by a very rich nucleosynthesis whose product is sort of dredged up to the surface and then transported out into the interstellar medium by massive stellar winds. And in this way, making them available for the next generation of stars and planets. So, I'm learning this now. So stellar winds are very important. And the general sort of consensus in AGB research is that the stellar winds are the mass loss mechanism of stellar winds is a two-stage process. In the first stage, stellar pulsation and convection, because AGB stars are variable stars and highly convective. So stellar pulsation and convection induces strong shock waves in the extended atmosphere, and these shock waves levitate and compress the gas. So what you're seeing here is a schematic picture of this. So on the y-axis, you have the radial distance from the star. On the x-axis is time. And here you see a mass layer. Oh, sorry, not something. Okay, I don't know what's happening. Okay, so a mass layer is accelerated by a passing shock wave, and then lifted and compressed. And if this mass layer reaches a distance where the temperature is cool enough for dust to form, then this mass layer can be accelerated. Help up here. Then this mass layer can be accelerated by radiation pressure on dust. And then we have a dust-driven outflow. If it doesn't reach such a distance, then it just falls back onto the surface of the star, almost like in a ballistic trajectory. Oh, I'm almost not touching. Okay, so in this second stage, the radiation pressure on dust particles, so the dust grains, they gain momentum when they interact with the stellar photons. So they can either absorb and re-emit photons and gain momentum, or they can scatter photons and gain momentum. And then this momentum is then transferred to the gas by collisions, and then you can have a general mass outflow. Okay, let me do this correctly here. So the Darwin wind models are 1D spherically symmetric description of the atmospheres and winds of AGB stars. So meaning that they're purely radial outflows. Wait, it should be like this, sorry. So it is a hydrodynamical model. So it includes the equation of hydrodynamics. And this is to take care of the propagating sound waves and shock waves that form in the atmosphere. It includes frequency-dependent radiative transfer, which is important to take care of opacities of molecule and dust that form in the extended atmosphere. And then, of course, it has a description for time-dependent grain growth. So what you're seeing here, the movie that I'm showing is a cross-section of a Darwin model. In this case, I think it's a carbon model. But here you can actually see, so in gray, this is plotted, is the gas density here. And overplotted is, in orange, is the dust density. So here you actually see what I was trying to explain in the previous plot, is that you have the gas is lifted outwards and compressed here, out now, and then the star contracts, and you have the star contracts, and then the temperature drops. And that's when dust starts to be formed. That's when you see. So you have there, it's expanding, and then the star contracts, and then dust starts to form. Okay. Okay. So the input models for Darwin, so model is, of course, it starts from a static hydrostatic atmosphere with defined by the basic stellar parameters. And then you vary the inner boundary to simulate a pulsating atmosphere or pulsating star with pulsation parameters describing the period and the amplitude. So X-wings, one of the main scientific goals of X-wings is to improve this description by using, with a combination of 3D models and observations. So I want to recommend that you look at poster number 1 by our PhD student, Arif Ahmad, who has self-excited pulsation of AGB and red supergiant stars in global 3D models. And then Michele is also speaking later today about pulsation models. And then we also have dust parameters. Okay, so what do you get out from the Darwin models? Well, observables that can be derived are, of course, wind properties, such as mass loss rate and wind velocity. So this plot here on the right is shows the mass loss rate as a function of time. This time is given in periods. So generally, we take the average of this. This is a quite extreme model because the mass loss rate is varying a lot. We can also produce gas to dust mass ratios. Here is the gas to dust mass ratio on the x-axis, and then it's sorted according to effective temperature. As you can see, most of our values actually lie from 500 to up to 200, no, from 500 up to 2000, which is a lot higher than the standard value of 200 that is often used. We can also produce spectra and photometry and disabilities by doing post-processing on the atmospheric structures. So here is an example of an SED over pulsation phase. So you see that it changes. This is the original hydrostatic model, and the dynamical model with dust is quite different. And then also that it changes over phase, over pulsation phase. Okay. So I added this slide because if there is anyone that's not so familiar with HEB stars, but there are two chemical types of HEB stars, or there are two main chemical types of HEB stars, and then there's intermediate types. So HEB stars start out as M-type. They have an oxygen-rich chemistry. So whatever is sort of, so carbon and oxygen is tightly locked in the CO molecule, and whatever is left over will dominate the chemistry of the star, molecules and dust. So as the HEB star evolves, it might change for a certain mass range. It might dredge up so much carbon that the chemistry becomes carbon dominated, and then what's left over here is carbon instead. And then you have a carbon-based chemistry, carbon-based molecules, and so on. This is a very schematic picture, but and there are intermediate types. So the Darwin models for C-type HEB stars. Here, the wind is driven mostly by photon absorption on amorphous carbon grains. The wind in carbon stars depend very critically on C-O. I call this carbon excess. So the carbon that is left, the carbon that is available for dust formation. So most carbon is locked in the CO molecule, but whatever is left over, carbon that is found in C2H2, C2H, C2, is available for dust formation. So we describe this sort of value C-O with, we call it carbon excess, and this is sort of a critical parameter. And when you construct models, you have to say what carbon excess you want to have, and you can explore different carbon excesses. The formation of amorphous carbon grains is described by classical nucleation theory in the Darwin models. Then for the M-type, here the stellar wind is driven by photon scattering on large iron-free silicate grains. It was long a discussion what drives the wind in these stars, but we seem to reproduce both wind properties and photometric properties with this driving mechanism. Now, in M-type HEB stars, there is no easily implemented description for how these dust grains grow or nucleate. So we use pre-existing seed particles that grow when conditions are favorable. For M-type HEB stars, there are actually now 3 different versions of this model. So there is a version with purely iron-free silicates, pure MgSiO4 only. This is the version that we have large model grids of. Then there also exists a version that includes alumina grains. They form where alumina forms the core of the dust, and then MgSiO4 condenses on the mantle on top of this. Now, alumina affects the structure of the atmosphere, but it cannot drive a stellar wind alone. alumina has too low abundance at solar metallicity. And today we're presenting a new model, even a third model, which has a model with growth of silicate grains with variable iron to magnesium ratio. Wait. Okay, and then for a more detailed description of this Darwin model, please check out the poster number 8 by Susanne Höfner, Gradual Iron Enrichment of Silicate Dust in AGB Star Winds. So there you can get more details about how this model is constructed and so on. Yes. So. Okay, let's do it like this. Okay, so one of the problems with the models using only iron-free silicates is that they produce a spectra without the iron, the silicate features. So what you see here, plotted in this plot, is in red is a spectrum, it's an SED of a model with purely MgSiO4 grains, iron-free silicates. And we reproduce very well the near-infrared and visual photometry. I will show you later. But obviously here, the silicate features are missing. And we have been playing around with this quite a lot, and it turns out that the grain temperature of these pure iron-free silicates is too low to produce a feature. The grain is there is enough dust, but we just don't see it because the radiative equilibrium is totally dominated by this region for iron-free silicates. They almost have no, very transparent here. So by adding a little bit of iron in the formation of the grain, we can see suddenly the silicate features pop up here. And it's a very, very small fraction of iron. The iron for this model, the iron to magnesium ratio is 0.04, and the condensed iron is just 2%. So very little iron, and then these nice features pop up. So it's important to say that the iron-rich silicates still accelerate the wind. They form close to the surface. They are needed to start to accelerate the outflows, and then the iron enrichment, very small iron enrichment, takes place in the wind on the surface of the grains. Okay, so we have been looking very much in this region before, visual near infrared, because this region constrains the wind mechanism. This is where this is the region where photons contribute most to the radiative pressure. So remember that short wave, these photons are more energetic. But now we hope to expand our search or our comparison to observations by looking into the mid-infrared, and hope that if we combine these two, we can constrain the wind mechanism, but also the grain composition and the amount of dust. Okay, so I'm going to do both at the same time. So one of the most important results when we started doing winds driven by photon scattering is that we could actually reproduce this very special trend that you see in M-type AGB stars. And so what you see in this plot is the observed photometric variation in oxygen for a few stars here, they're marked here. And they show very distinct trends, that you have a wide variation in V minus K here. So check out note the scale. So there is a huge variation in V minus K and little variation in J minus K. And this was sort of proof that, or a very strong indication that we were correct with thinking that it could be driven by photon scattering, because if this is caused by molecular changes, and if you have a transparent material, you can actually see these changes. And the new models, the one with gradual enrichment, also reproduces this trend with wide variation in V minus K and small variation in J minus K. Okay, so we're also looking at, as I mentioned, we want to look at mid-infrared colors and photometry. So this is an example from Spitzer, from a Spitzer IRAC color diagram for the same models. These are the models with iron enrichment. These are the corresponding hydrostatic models. So what's important to see here, first, that the dynamical models and the hydrostatic models are differ, because we take into account more of the molecules here, and that they change, the photometry changes with phase. Now, they look very nice and elliptical, but take this with a grain of salt. They could not be fitted super well with the sinusoidal variation, but I wanted to plot it like this just to give you an idea of how much it changes and so on. The red colors in 5.8 minus 8 here, the ones that are most red, is caused by, if you have a very wide or strong 10 micron feature, silicate feature, then this bleeds into the 8 micron band. Let me go back. So here you have the IRAC band, and this feature, when it's very strong, bleeds into the 8. And then you get really red colors in Y here. The variation in X is probably due to water, but we're still looking into this. Okay. Okay, so then on to something else. So we have done some, this is from 2019 investigation I did about wind properties for C. Darwin models, carbon. So now we're moving to carbon models at different metallicities. So mass loss rate. So what you see here is mass loss rate for a small grid, I would say, of solar mass models. They all are wind producing. And then the models have different metallicity, but same stellar parameters and same carbon excess. So that means that the C over O is different. And then I compared, so what you see here, solar versus LMC, the mass loss rate of these. And if they lie on this diagonal, they are similar. I don't know what's going on. Okay, so, but basically, so what you see here is that the mass loss rate for these models, I mean, if they have the same stellar parameters and the same carbon excess, the same available carbon to form dust, then they produce pretty much the same mass loss rate. So it's the available carbon that is very strongly affecting the mass loss rate. And now so it's a question to stellar evolutionists so the dredge up of carbon might of course be metallicity dependent. And then lastly, we also produce mid-infrared photometry for this grid. So it's so this is spitze-photometry for the solar mass grid that I showed you in the previous plot. They all have wind. The metallicity is sort of solar, and then it's supposed to mimic LMC and SMC. And they also have the same parameters, but different carbon excess. So C5, C6, C7 is our notation for different carbon excesses. Here you see them. But so you have 3.6 minus 4.5, and then 5.8 minus 8. And
sorry to interrupt, you're just running out of time.
Yeah, okay, so I'm just going to finish this and then. So basically the metallicity does not affect, as with the wind properties, the metallicity is not strongly affecting the resulting photometry, whereas it's mostly decided by how much free available carbon you have for grain formation. Oh, and this, sorry, I just have to say, this was done by my master student last year, Bladh. Okay, so now I'm done. I skipped the summary. And then I just say that we have postdoctoral positions available at postdoctoral position available at Uppsala. Please apply if you are interested, and then also check out poster 7 by Mayora.
Okay, thank you, Sara. We have time for a few questions. So if you have a question, either raise your hand or type it in the chat. Ju, you have a question. Would you like to ask it verbally? Okay, I guess not. So Ju says, hi, Sara. Thank you for the informative.
Sorry, I think there's one question from Ranjan. Is that right?
Yep, but we'll just go through Ju's question first.
Okay.
So he says, I believe the Darwin tool is a very powerful tool in studying AGB wind. I have some questions about the model of the Darwin code. Dust formation is tightly coupled with non-gray radiative transfer. Does Darwin treat non-gray radiative transfer self-consistently?
What does it, yeah, I think, what does it mean by that?
Well, I'm not sure you can see the question in the chat. Does the chemistry and thermodynamics couple with the non-gray radiative transfer code? And how does Darwin solve the radiative transfer equations?
Yes, I think so, yes.
Okay, Ranjan?
Yeah, hi, Sarah. It's nice talk. I just wanted to confirm about this Darwin model. In one plot you showed about this density of the mass versus dust. I mean the star versus dust and the temperature. So does that have different things with carbon stars and MCS stars and M stars? They are for same. Sorry, can you get my question? Hello?
I could hear it. Sarah, did you?
No, I do not understand the question.
Okay, so there was one plot versus temperature versus rho G by N. So in does that plot includes both C-type and M-type stars, or is it for separate? I mean, that's separate.
Is it the dust to gas ratio?
Yes, dust to gas ratio.
Oh, okay, sorry. This plot was from the it's from the large grid of M models. So this is M models. Yes.
Okay, thanks. Okay, so I had one other question about this, your last slide, where you showed the Spitzer modeling. Do you have any observational verifications? I mean, the observational data is also available for C-type stars for solar and LMC. So did you verify it with the observations, or those are just modeling and in preparation?
Are you asking if these values are sort of
Yes, yes.
so we did look at different observations and they agree. We're in the right ballpark. There is a publication by Olivia Jones looking at, I think it was M32, which I think is quite close to solar. And then we're lying, I think, in the middle of her, right on her values. But there is in the observations, there is a large spread in the observed values.
Yeah, because in solar part, most of the I have not worked with this Darwin model, but
Sorry, Ranjan.
solar has get disturbed. Okay,
Sorry,
we can talk later.
We've run out of time for more questions. So sorry for the people with their hands up. You can ask Sarah in the Slack. So make sure you all join that. Next up, we have Ambra Nanni, who will be talking about dust production around carbon-rich stars and the role of metallicity. So Ambra, feel free to start sharing your screen.
Can you see that?
Yep, looks good.
Okay. So, okay. Hello, everyone, and thanks for giving me the possibility of talking today about this work related to dust production around carbon-rich stars, and in particular on the role of metallicity in this process. These are the people that mainly contributed to this work. So, yes, just to start with, we have seen with Sarah that we have two types of AGB stars. So we have oxygen-rich and carbon-rich stars. Carbon-rich stars are characterized by the fact that the C overall ratio is greater than 1. So all the oxygen available is locked in the very stable CO molecule, and we have an excess of carbon, free carbon in the atmosphere of these stars and in the circumstellar envelope. This carbon excess is due to the fact that we have the Death-throes processes, which have an efficiency that depend on the metallicity and on the mass of the star. So given that we have free carbon in the atmosphere, we have in the atmosphere acetylene molecules from which we can form carbon dust. On the other hand, we have also other compounds such as silicon carbide, magnesium sulfide, and maybe iron. So basically, the acetylene and amorphous carbon content are related to the carbon excess, which depends on the efficiency of the Death-throes. And on the other hand, we have that the other compounds are their production is more or less proportional to the initial metallicity of the star. So given this, we know that in local galaxies, and in particular in the Magellanic Clouds, we have plenty of observation of carbon stars. And we have that these stars are particularly relevant for the dust enrichment and chemical enrichment of these systems. And also we have that carbon stars are among the red stars, so they really shape the color magnitude diagrams of these galaxies. We expect to have more data coming soon from the JWST, for example, for low metallicity galaxies, so more data will be available. For a fraction of these carbon stars in the Magellanic Cloud, we also have Spitzer spectra, and people have analyzed this, and in particular, they in a series of work, they use the Manchester method. And with this Manchester method, they were able to derive some information in relation to the acetylene feature. So we have information about the acetylene content, mainly from this feature that we have around 70.5 microns, but also we have some information about the silicon dust component, so by studying its feature around 11 microns. And we can relate these features, the properties of these features, with the reddening of the star. So basically, we can relate this with how much dust we have in the circumstellar envelope. And this is done by looking at this color here using these two bands that, as you can appreciate, are rather independent. They are not affected by any feature, more or less. So this is a good probe. This color is a good probe for the reddening, so for knowing how much dust we form in these stars. So once people analyze this, they basically look at the mean equivalent width of the acetylene feature as a function of basically the dust content in these stars, and they found that there is a trend between this equivalent width and the metallicity. So they have looked this for Milky Way, carbon stars, LMC and SMC. So for decreasing metallicity, they found that the equivalent width of the 70.5 microns feature tend to increase. And on the other hand, if we look at the feature strand, the SAC feature strands with respect to the continuum, we find this other trend. They found this other trend, and basically also in this case, we see that the strength of the feature increases with the metallicity from the SMC to the LMC. So there is again a trend with the metallicity, even if in this case we have stronger feature for higher metallicity, but we also have a trend with the, if you wanted, the mass loss or the dust production rate. And this trend changes with the metallicity, and it will be, of course, also related to the star formation history of these systems and so on. So we need to interpret these trends, and in order to do so, we should couple dust formation models with the stellar evolutionary models that take into account the fact that the property of stars are changing along their evolution. So we don't just have that parameters are just changing one at a time, but we have a full evolutionary model. And also, we need to take into account that the stellar evolution will depend on the initial metallicity of the star. So something else that we don't fully understand yet is how the expansion velocity changes with the metallicity. So if we look at the galactic measurement with respect to the Large Magellanic Cloud measurement, we see that at lower metallicity of the Large Magellanic Cloud, the expansion velocity seems to be smaller with respect to the galactic environment. So we can think there might be a trend with the metallicity. Unfortunately, we don't have many data, and so we are not able really to have a full picture of this. As we have seen before, also theoretically from the hydrodynamical model was found that this expansion velocity should depend on the carbon axis. So it seems not to be related to the metallicity, but however, the data are indicating also this possibility. So why is depending on the carbon axis is because the expansion velocity is because basically when you form carbon, you accelerate the wind. So that's why the expansion velocity is proportional roughly to the carbon axis. The motivation of this work was to interpret these observations. So in particular, the acetylene and SiC content and wind speed as a function of the metallicity by employing models of dust growth coupled with the stationary wind and combined with stellar evolutionary tracks. We use the fruity stellar evolutionary models for this work. So now I will just tell you something about the models, how they are built, and the constraints that we put so far to these models. We have that we follow dust growth for several dust species coupled with dust-driven wind. And basically, this is what have been done initially by Ferrarotti and Geil 2006, and was also used by other groups such as the Roma group. And recently we updated this model by including the time average effect of shock. So this is particularly relevant, for example, in the inner part of the envelope where the density will be enhanced. And this is critical for the formation, for example, of silicon carbide. This follows more or less Cherchen et al. 1992, even if there are some modification to this model. And finally, we can couple the results with a radiative transfer code in order to get the spectra. So the input quantities of the model are the stellar parameters that are taken from the stellar evolutionary tracks. We have to decide something for dust optical properties, and in this case, it's particularly critical to choose the right optical properties of carbon dust. On the other hand, we have another parameter, which is the seed particle abundance, which is critical because affects the grain size, and so again, the optical properties of our grain. This seed particle abundance is uncertain, so we have to assume it, and in our model we tune it to reproduce the observations. So we just assume seed particles are there and we follow just the process of grain growth. Basically, what we get as an output is the characterization of the circumstellar envelope, and in particular, dust composition, the dust production rate, the wind speed, and the spectra. So we can compare our model prediction with observation and constrain our assumptions. So this is what we have done in the past, and basically we constrain the dust optical properties of grains and their size by selecting those optical properties and grain size which simultaneously reproduce the infrared photometry and the photometry from Gaia data release show. We use these optical properties to build our model in a grid, in a large grid, and we fitted the spectral energy distribution of carbon stars in the Magellanic Cloud through the models. In particular, we have fitted around 3,000 carbon stars in the SMC and 8,000 carbon stars in the LMC. And we derive for this by comparing the photometry, by fitting the photometry through our model, the mass loss rate, dust production rate, and gas to dust ratio. And you can see the results here in the right. We have for LMC and SMC, the mass loss as a function of the gas to dust ratio. So this was one of the constraints, and recently, as I was mentioning, we took into account the shocks in the circumstellar envelope, in particular in the inner part of the wind, and as constraint, we basically we put constraint by considering the size distribution of presolar grains, and here in the right we compare the observed distribution with the one that we derive with the models, with a certain assumption for the seed particle abundance that you see here. So we fairly well reproduce this size distribution by employing this updated model coupled with the fruity evolutionary tracks. This grain size distribution is reproduced by stars of masses around 2 solar masses and solar metallicity, and you can find more all the details in this work by Sergio Cristallo. Now I will go to the results connected to the acetylene, silicon carbide, and wind speed. So we start with this plot. That was the first one that we see. And so we run our model along the track, and this is what we obtain for stellar mass of 2 solar masses. This is the acetylene injection rate, and here we have the optical depth at 1 micron. So we use basically the acetylene injection rate as a proxy for the equivalent width, while for instead of using this color, we are taking into account the optical depth at 1 micron. And so we did this for different metallicity, from the Milky Way to down to the SMC metallicity, and we also added the case for galactic halo, so low metallicity that can also be representative of dwarf galaxies, for example. And so we find that the trend of our model are in qualitative agreement with the observations, and in particular we have that given the fact that the lower metallicity we have more efficient earth drop, we bring to the stellar surface more carbon, and as a consequence we have both more acetylene and more carbon dust. However, the acetylene content increases because the amount of carbon dust remains low enough to allow to see this trend, because at one point when you form carbon dust, you accelerated the wind and you cannot form dust anymore. So the thing is that you cannot form carbon dust without any limit. You are limited by the fact that at one point the wind will be accelerated, the density drops, and you cannot form carbon grains anymore. And so we see this kind of trend. We look at this also for the three solar masses cases, and we find a similar trend, even if the values that we obtain are different, are higher. We have higher acetylene content because of the fact that we have more efficient dredge up. Also, we can look at both the cases here in the right, and again look at this plot, but also we can look at the individual observation, not just to the average value, and we will notice that there is a large scatter in the observation. If we look
sorry, Ambra, you're running out of time. If you could just finish up.
Wasn't it 15 minutes? Because I am 13 minutes according to my time.
Oh, I thought we started 1 minute late. Sorry, continue.
Okay, so we have a large scatter, and as a consequence, we have that the spread that we observe in this plot can be reproduced by the fact, can be explained by the fact that we have two different stellar initial stellar masses. So if we look at this other plot, we can compare with our results, and we find that for a given optical depth, there is a clear trend with the metallicity, as observation indicates, and also as it was expected by the theory. So this is rather independent on the stellar tracks used and is in agreement with previous works. So finally, just to tell something about the expansion velocity, we compare the expansion velocity as a function of the luminosity for different metallicity given in the different panels here, and we have different initial stellar masses. So as you can see, we fairly well reproduce the expansion velocity, and we also notice, however, that for different initial masses, we have different trend for the expansion velocity at varying metallicity. So for the three solar masses, we have that if we lower the metallicity, the expansion velocity would actually tend to be lower. And this would be aligned with the fact that we find a lower expansion velocity at lower metallicity. This is not, however, a direct effect of the metallicity, but rather is an effect of the stellar evolution, because for the three solar masses, if we lower the metallicity, we get hotter stars, and so we produce less dust, and we produce it farther out from the stellar envelope, and the acceleration is lower. So in this case, we are not dominated by increasing carbon excess at lower metallicity, as instead happens if we look below two solar masses, for which we see that the expansion velocity increases with the metallicity, and this is because of the fact that in this case, we are dominated by the fact that the dredge up becomes more efficient. So these are my conclusions. Thanks for your attention. So we couple our dust model with the stellar evolutionary tracks from Fruity, and we are reproducing qualitatively the observed trend. Next step will be to compute the full spectra and to make a better comparison with the observations. We want to push this forward in the framework of galaxy spectral energy distribution modeling, and this will be done in the framework of the Dingle project at NCBJ that will start in May, and that has been recently founded by the National Science Center in Poland. So there will be a PhD position announced very soon. I think it is a matter of days. And we have also postdoc positions, and you can find them at this website. Please feel free to contact me anytime if you are interested. Thank you.
Okay, thank you, Ambra. So if anyone has any questions, please raise your hand or type in the chat. Sophia Ramstedt has a question.
Yes, thank you for a very nice talk, Ambra. I was wondering, so I saw when you compare to the observations that you used, the ALMA observations from the LMC, and there are rather few points and probably will not, I mean, there's for sure a limit to how much CO observations you can do when you want to move towards lower metallicities. So if you want to observe other galaxies, you will definitely need another probe. So I was wondering, why are you not including OH maser observations, for instance? I mean, they might be not exactly representative of the final expansion velocity, but they should at least give you a hint of what the expansion velocity will be.
We can for sure look at this. I didn't check so far, but yes, of course, there is the problem that we cannot go too much further out and we cannot look at too low metallicity, so it will be difficult to constrain the models. And yes, of course, this is an issue and we need to look at something else, and for sure I can better look into this as well. Thank you.
Okay, thanks, Sophia. Any other questions? One from Theo.
Hi, thanks for the nice talk. I was just wondering, at some point you mentioned that you showed this plot where you had the dust to gas ratio, but I couldn't really read it very quickly. And I was just wondering, well, first, did I understand right that the way you constrain the dust to gas ratio is just based on the models, whatever the models give, is not a direct observational constraint, and by observing the gas and the dust? And the second question is, what range of dust to gas ratios do you find?
Yes, so basically what I'm doing is computing the dust production, and by computing, in order to compute the dust production, I need the stellar parameters, and among the stellar parameters, I also need the mass loss rate, because it's not something that my model can predict. So from this, we have a grid of model and a grid of spectra, and then we basically fit the observed photometry to the spectra, and then going back to the models, we can kind of constrain the dust to gas ratio. So is of course model dependent, but we also get a good agreement with what hydrodynamical models finds. For example, I didn't show it here because it was not the focus of the talk, and the range that we get is quite large. We go from very high gas to dust ratio, so corresponding to almost dust-free stars, down to I think okay, this also depends, of course, if you're looking at the SMC, LMC, because for the LMC I find some stars that are more dust enshrouded, down to I think 200, if I remember correctly, and for the SMC down to 500, more or less. The average value, I think, that was 700 for the LMC. And this, of course, depends on the fact that you have also different star formation histories. And so you can have the stars have different properties when you look at them.
Can I ask something follow-up, Thaisa?
We've run out of time. Can you ask it in the
Yeah, I'll ask later.
Sorry. Thanks, Theo, and thanks, Ambra.
Thank you.
The next speaker will be David Gobrecht, talking on the nucleation of metal oxides in AGB stars. So David, you can start sharing your screen.
Yes. Hello, everybody. Can you hear me?
We can hear you, yes. We can't see you, though.
Start my video. Yes, okay. Now you should be able to see me as well.
Yes. Don't worry, we can't see the Zoom things on your screen.
Okay. Pause share, resume.
You are sharing. You just need to go into like presentation mode.
Okay, that should be like this now. No, it doesn't work. Slideshow, start from first slide. Sorry again. Share screen, desktop. Okay. Now everything is right?
Yes, go ahead.
Okay. Thank you, Thaisa. As you said, I'm talking today about the nucleation of metal oxides in AGB stars. So what is dust formation actually all? Sorry, guys. What is dust formation all about? So dust formation, it is induced by a process which is called nucleation. And in contrast to many authors, I consider actually dust formation not as the dust growth of pre-existing seeds, but really as the formation out of the gas phase. But how do we model this kind of gas to solid phase transitions? And there I want to say actually the chemistry or chemical reactions are key. And what I want to address next is actually whether equilibrium is a valid assumption for dust formation or not. So if we have a look at thermodynamic equilibrium, we can actually split that up into 4 components. One of them is the mechanical equilibrium, or also called hydrostatic equilibrium. This is actually given by a constant radius or by the equilibrium of inward directed gravity pressure and outward directed thermal, or in some cases radiative pressure, that actually keep the star in its spherical shape. Then as a second component, we have the thermal equilibrium, which is actually characterized by an equal T for all species that are present in the circumstellar envelope. And then we have a third component, which is the chemical equilibrium, which is actually characterized by a minimal total Gibbs free energy. You already see this Gibbs free energy. It depends on temperature and pressure, and so somewhat is connected to the mechanical and thermal equilibrium. And as a last component, we have the radiative equilibrium, which actually says that the luminosity is given by the law of black body radiation, and that the temperature also is related to a maximum wavelength or frequency. Well, the question is whether thermodynamic equilibrium is valid in AGB atmospheres. And well, that is obviously not the case, because we have in a mechanical or hydrostatic equilibrium, we have the deviation because stars pulsate, which is known since more than 100 years. Also, the thermal equilibrium doesn't seem to work, since we have different gas components can have different temperatures, but also gas and dust have definitely different temperatures. That's why thermal equilibrium doesn't hold. Well, if we look at the chemical equilibrium, we find actually HCN and CS in oxygen-rich AGB stars, which is in contrast to the statements that in oxygen-rich stars only carbon monoxide as a carbon-baric molecule should exist. And vice versa, we also find water vapor and silicon monoxide in carbon-rich AGB stars, which is in contrast to the prediction of thermodynamic and particular chemical equilibrium. And also in the radiative case, it's actually, we see that we have emission of masers, which clearly shows departures of radiative equilibrium. So dust formation equilibrium, it's a nice try, but it's actually contradictory, because actually you try to form something out of equilibrium, which is, at least in my opinion, that's contradictory. Moreover, you might try to put one or the other of these 4 components into equilibrium by arguing with time scales, but you also have some severe drawbacks if you do that. On the other hand, you can say, okay, we apply the equilibrium, for example, to the innermost zones of the star, because there the densities and temperatures are sufficiently large to ensure thermalization by collisions. And if we look at the innermost part of the circumstellar envelope, then we find actually matter mostly in the form of atoms and gas phase molecules. And as we move further out away from the star, the densities and temperatures get cooler, and matter of growing complexity can form, and that consists of nanoparticle clusters and dust grains. So, as I said, the innermost part can be maybe treated with equilibrium, However, the ideal goal would be just to treat everything in non-equilibrium. But this is quite a challenging task, and there have been several approaches. Jels Boulanger, a previous PhD student of our department, tried to couple these three first sorts of matter in a chemical kinetic approach. I tried that myself with coupling equilibrium and non-equilibrium via the gas phase molecules. And the ideal goal would be indeed to couple everything in a non-equilibrium way, or just to find a very good limit to put the constraints of equilibrium and non-equilibrium very close to the star. Moreover, we have actually the problem that also here in this dust formation zone and also beyond, we have also atoms and molecules present. So we have a coexistence of all of these species. So I talked now a lot about equilibrium and non-equilibrium. So how do we treat this dust nucleation? So on one hand, we could use classical nucleation theory, but on the other hand, classical nucleation theory uses as a basic principle actually supersaturation. And that means that dust formation or condensation can only occur when the concentration or the pressure of a dust forming component exceeds the equilibrium pressure. And already you see here, equilibrium is already named. So it's actually not one of my favorite theories. So what is actually classical nucleation theory or CNT about? Well, it's a top-down approach of a spherical dust grain with a homogeneous interior. And if you have a look at this, starting from large dust grain sizes, you actually have here a curve that is characterized by a single energy dependence of the particle, which in the end up is characterized here by a certain critical grain size, which has the largest energy barrier, which actually corresponds to the bottleneck in the classical nucleation theory. And this single proportionality called surface tension, actually you can describe that in terms of particle size as a dependence to the cluster size and to the -1/3. And if we compare this, actually this classical nucleation prediction, the energy depends with cluster data, with a homogeneous bottom-up nucleation that we look together with Jels, then actually you see that, well, all over these cluster energies very roughly follow, which are here depicted in the violet line, very roughly follow this red line, which corresponds to the classical nucleation theory fit. However, if we go in further detail, we still see here for all four different kinds of dust species that we actually considered, that we have a certain deviation between our cluster data and the classical nucleation prediction. And you might now say, well, this is not a lot here. Maybe, for example, that would be 20, 30 kilojoules per mole. I remind you, however, that here, this is a normalized cluster energy. This is normalized to the cluster size n, which actually means that you have to multiply this value here by 6. So which 20, 30 kilojoules per mole would already raise to 150 or 180 kilojoules per mole, which is actually quite considerable. So you might say, okay, we use still not only n to the -1/3 classical nucleation dependence, but we increase that, put another factor, and you can do that, and you will see that the fits gets slightly better in all four cases for all four nucleation candidates. But there's still some drawbacks because you will have some more stable sizes and some bottleneck sizes, which are here displayed in this kind of wiggly structure of these cluster energies. So that was all done with homogeneous clusters, so meaning one certain species of dust or of dust clusters. You can also do that in a heterogeneous way. And if you do that, then you could start in saying, okay, we have metal monoxides. Their structure is actually quite clear. They just have an oxide and a metal. And if you look at that, then you will find, okay, silicon monoxide is the most stable metal oxide, followed by titanium monoxide and aluminum monoxide and some other oxides. But the structures from those, they have no liberty or no freedom. This is just a diatomic molecule. You can move up and go to dioxides, and here I displayed titanium dioxide, which has a band structure. Here silicon dioxide, which has a linear structure. The structural diversity for the dioxides is not yet that big. I mean, here you have these square forms of the mixed metal oxide clusters here of Al2O2. But as you increase with sizes, you actually get a higher and higher structural complexity. And moreover, if you use many metals like I did, like with silicon, titanium, aluminum, calcium, iron, and magnesium, you will have more and more isomers and also more and more chemical compounds. And to give you an example, I show you here a silicon aluminum teroxide, which I calculated, and that actually can be characterized by its vibrational modes that can also be observed by their vibrational in the near infrared. And these actually give for all different kinds of clusters and structures, they give individual fingerprint spectra. So we really would be able to identify certain clusters owing to their vibrational emission. So I've talked now about classical nucleation theory, equilibrium, homogeneous and heterogeneous bottom-up nucleation. And we all saw that's all kind of difficult, and there are all some kind of drawbacks in these dust formation models. And why is that so? And in my humble opinion, I would just say because you try actually to solve a problem that is to a large part of quantum chemical nature with classical physics methods. And don't get me wrong, physics plays an important role. For example, as we have heard in the presentation of Sarah, that the momentum transfer of photons to the dust grains plays a crucial role to drive the mass loss. However, it cannot really explain the energies and the geometries of the nucleation species. And with that, I actually would like to come to my conclusions. And then actually that thermodynamic equilibrium is not valid in AGB stellar winds where the dust formation occurs, which actually implies that dust formation also doesn't occur in equilibrium. The supersaturation, a basic and footing principle of the classical nucleation theory, assumes equilibrium, and therefore it oversimplifies the energies and geometric structures of the nucleating species, which are also said to be molecular clusters. And these molecular clusters, including their chemical reaction rates, are key for understanding dust formation. And I want actually to end with a famous statement of Richard Statement, who said there's plenty of room at the bottom. Well, he meant it rather in a technological sense, but I interpreted it in a wider sense, just saying, okay, at the nanoscale, we have quite a lot of things to discover still. Thank you for your attention.
Okay, thank you, David. If anyone has any questions, put your hand up again. Suzanne Höfner? Go ahead.
Hi, David. Very good talk. That takes me back a few years. The question is basically, if you're in the shoes of a dynamic modeler, would you prefer to use seed particle abundances as a parameter, or would you go for classical nucleation theory? Because I mean, you have to start somewhere.
Yes, so I would really start at the molecular level and try to start these seed particles.
Yeah. I know you for modeling it, but if you want to do wind models right now, and you have basically these two approaches, especially for the carbon stars. So we have done classical nucleation, say a la Geil and Seelmeier, but you could also just set the seed particle abundance and go from there and do the growth. And I always make sure to distinguish between nucleation and growth. I think no others don't. I have come to the conclusion that the second thing is actually the cleaner thing to do, because then you're admitting there is a freedom in the model, so to speak, as opposed to saying, okay, we do classical nucleation and everything is fine. But I don't know what your take would be on that.
Well, I think in the carbon-rich case, it's probably still easy, because carbon just can nucleate on its own, and so there's actually, yeah, I mean, once you said, okay, you're over a critical size, you can just use a seed particle abundance. I would say in the oxygen-rich, it's going to the chemical diversity. This is, yeah, a less safe assumption, in my opinion.
Okay, thanks.
Thanks, Suzanne. Thanks, David. Does anyone else have another quick question?
Hi, Thaisa. Sorry, my hand won't raise for some reason. I can't find it. David, thanks for the talk. I was wondering, you showed how your calculations change with the classical nucleation theory for the energies. And I was wondering if you've propagated that down to look at how have an idea of how this would affect the things that we're interested further down the line. So the mass loss rates, the wind driving, the dust opacity. Do you have an idea of how big the difference is compared to the classical nucleation theory?
Well, yeah. As you said, thank you. I compared the energies. So if we kind of convert that into nucleation rates, then I just have an example where, for TiO and TiO, so the smallest nucleation of titanium dioxide, namely the monomer plus the monomer, there actually chemical kinetic reaction rate has been derived by John Plain, and that is orders of magnitude slower than what you would get if you assume classical nucleation theory and derive nucleation rate according to this.
So the dust would form much slower, you think?
Yes.
Okay.
In the initial process, yeah.
Okay, cool. Thank you.
You're welcome.
Thanks, Shazrin, and thanks, David, for that nice talk. David, if you could stop sharing your screen now. Our next presentation is from Mehdi van der Sande, talking about dust gas chemistry within AGB outflows.
Hello, everyone. So I see you can see my screen and hear me.
Yes.
Okay, let's start. So I'd like to thank my fellow organizers for giving me the opportunity to discuss the effect that the dust that we already heard so much about can have on the chemistry within AGB outflows. So first of all, an AGB outflow is a very rich astrochemical laboratory. So close to more than 100 different types of molecules have been detected so far, as well as some 15 types of newly formed dust grains. As you already heard, the type of chemistry depends on the elemental carbon to oxygen ratio of the star itself. So C over rho, larger than 1, carbon rich, smaller than 1, oxygen rich chemistry. And then in between we have S-type stars. The outflow can be divided into 3 main regions, each characterized by specific chemical and dynamical processes. And these are tightly linked throughout the outflow. In the inner wind, the chemistry is taken out of equilibrium because of shocks caused by stellar pulsations. Then a bit further out, dust is able to condense from the gas phase, and it's in this region that the wind is launched. And then finally, in the outer winds, the material has reached its terminal velocity. And in this region, the chemistry is mainly photon-driven. Because of the lower density, UV photons of the interstellar radiation field can more easily penetrate this region and cause like an interesting chemical reactive soup. When it comes to chemical models of HGB outflows, they can be divided into two main types. So either they deal with a non-equilibrium chemistry up to the point of dust formation, or they are geared towards the photochemistry of the outer winds. These outer wind chemical models are chemical kinetics models, and they include only gas phase reactions. And we have included comprehensive dust-gas chemistry in such an outer wind chemical kinetics model. So our new model is able to describe the chemistry of the outer wind as well as that of the dust interaction. So as you can see, we've been having quite some fun with it. So, well, we've included these dust-gas chemical reactions to be more chemically complete, but at the same time, and more importantly, also to try help explain some strange observations. For example, in high-density oxygen-rich outflows, SiO and SiS are seen to decrease in abundance before the onset of their photodissociation. There was also these trends with mass loss rates in oxygen and carbon-rich outflows, where CS, SiO, and SiS decrease in abundance with increasing mass loss rate. This again points towards depletion onto dust grains. And moreover, we actually have observations of water ice on top of the dust in OH-IR stars. So let's include some dust-gas chemistry. We allow for gas phase particles to accrete onto the dust, and this way they form an ice mantle. It's a physisorbed ice mantle, so it's not actually part of the dust. Once on the surface, reactions can still occur, either via the diffusive Langmuir-Hinchelwood mechanism, where ice species hop around, meet and react, or the stick and hit Eli radial mechanism, so gas phase species bumping into an ice species and reacting. The ice can be destroyed via thermal desorption, where the dust is too hot to handle, or photodesorption, where a UV photon knocks off an ice particle and pumps it back into the gas phase. And we also include a mechanical sputtering, so collisions with gas phase molecules can chip away some of the ice. The main assumption of our model is that dust is present. So we do not form dust, we assume it's already present, and it has a certain grain size distribution. And for that, we use the canonical MRN distribution. Now that the scene is set, let's take a look at the effect dust-gas chemistry can have on the gas phase composition. Here I show you the fractional abundance of water throughout various oxygen-rich outflows. The black line is for gas phase chemistry only. Different shades of blue are different dust-gas chemical models. The columns here are for different outflow densities, and the rows are for different dust grains. We find that the effect on the gas phase depends on 4 factors. First of all, the outflow density. As the outflow density increases, there are more collisions between dust and gas, so more accretion onto the dust or depletion from the gas phase. This is what you see here. In fact, we find that dust-gas chemistry has no effect for lower density outflow, so this corresponds with observations. There's also an effect of the dust temperature. As we go from cooler to warmer dust, the thermal desorption rate will increase, so there will be less depletion from the gas phase. Drift velocity also plays a role. If the dust is a bit faster than the gas, that's nice because there's more collisions, but it shouldn't be too fast. The drift shouldn't be too large because then sputtering starts to take over. There's a balance that needs to be struck. And finally, the type of molecule also plays a role. So water here has a very high binding energy. This means that it really likes to sit on top of the dust. CO and N2, for example, have low binding energy, so they don't really accrete onto the dust. So just the gas phase composition already tells you a lot about the effect on the gas phase. So as we deplete species from the gas phase, we accrete them on top of the dust. And this leads to the formation of an ice mantle. Here I show you the number of monolayers of ice on top of the dust in an oxygen-rich and a carbon-rich outflow. This is for a very high density outflow, so is a best case scenario. Different colors correspond to different types of dust. The main difference that you can see here is that oxygen-rich outflows easily achieve more than 100 monolayers of ice, whereas the carbon-rich one barely reaches 10 monolayers. This is partly because carbon-rich dust is a bit warmer than the oxygen-rich, but mostly because, well, oxygen-rich outflows contain a lot of water, and water really likes to be ice. So that's a compound effect that you can see here, dust temperature and just the composition of your gas phase. So we can conclude that dust gas chemistry has an effect on the gas phase composition. For high density outflows, we see that gas phase species can be depleted on top of the dust, and this in turn leads to the formation of an ice mantle. Now, these two conclusions, of course, lead to more questions. We have a question regarding the depletion of gas phase species, and then one regarding the ice mantle. Let's first take a look at the depletion and whether the grain size distribution can influence the level of depletion. We asked ourselves this question not just because it's an interesting question to ask, but also because it's quite relevant to AGB dust, since we don't really have a good grasp on the grain size distribution of stellar AGB dust. We know from observations and modeling that the dust is large and not single-sized, but the grain size distribution is still quite unknown. This has effects, well, ramifications for the AGB outflow itself because of the energy balance, but it also is important to the ISM, since AGB stars contribute about 70% of pristine stellar dust to the ISM. So if you want to understand the chemical and physical evolution of dust in the ISM, which a lot of people want to do, then having a good grasp on the input grain size distribution would be of much use. So can the gas help us constrain the grain size distribution? For that, we switched from DMRN to unMRN-like distribution. In both cases, the dust grain number density is given by this equation. So we have the minimum and maximum grain size, and then the slope of the distribution as parameters. In the MRN distribution, they are fixed to these values. And now in an MRN-like distribution, we let the 3 parameters run wild as free parameters. Here I show you the water and SiO abundance in an oxygen-rich outflow. Black, again, gas phase only. Different shades of blue are different slopes of the distribution. In the middle panel, I show you the results using the minimum and maximum grain size of the MRN distribution. On the right, larger grains, and on the left, smaller grains. And it's quite clear from this figure that the grain size distribution has an effect on the depletion level. So here for the smaller grains, see that there's much more depletion going on. And in fact, we found that the level of depletion depends on the average cross-section of your grain size distribution. This is visualized in this figure. So here on the y-axis is the depletion level. So this dip in abundance corresponds to a depletion level the other way around. This is for SIS, for different outflow densities, different drift velocities, different shades of blue are different types of dust. Sigma dust over S is our outflow independent way of saying the average cross-section of the grain size distribution. And you can see as we increase in cross-section, the depletion also increases. It flattens off after a certain point. This is because of a balance between accretion, thermal desorption, and sputtering. So if we were to retrieve such a depletion level from observations, we can only say something about the lower limit of the average cross-section of the dust. But this is still of use because almost in all cases, this lower limit is larger than that of the canonical MRN distribution. So we can still compare. And it is possible to retrieve the depletion level from observations. It's just not, just requires quite a bit of effort because you need to know the physics of the outflow a bit. Then you need to have enough molecular lines. So you probe the entire outflow. And then you need to do quite a bit of radiative transfer modeling to retrieve the abundance profile. Because of that, all these efforts, there aren't that many observed depletion levels available in the literature. We found some, here they are, and we were able to estimate the average cross-section from these observed depletion levels. And we found that they're all larger than that of the canonical MRN value distribution. So this implies that the production of large grains is accompanied by more small grains than expected. And these small grains correspond in size to ultra small silicates or PAHs. So let's go back to our overview slides. We found that the grain size distribution does influence the level of depletion. It depends on the average cross-section of your grain size distribution. We can use molecular lines as extra tools to determine the grain size distribution, which is useful for AGB outflows and also for the ISM. And from the literature, we found that the production of large grains is apparently accompanied by more small grains than predicted. So let's now turn our attention to the ice issue. And again, we're going to tackle this from an ISM-centric perspective, because interstellar dust grains are thought to have this layered structure of a silicate core surrounded by an inner organic mantle and then an outer ice mantle. The inner organic mantle is composed of refractory organic material, so aliphatic and aromatic carbon compounds. And these are thought to be formed through photoprocessing of interstellar ices, so baking the ice via UV rays. We were wondering whether this photoprocessing of interstellar ice, the formation of refractory organics, could already take place in the AGB phase. So instead of in the diffuse ISM, in the prenatal phase of interstellar dust, the AGB phase. And to that extent, we included a new reaction, namely the photoprocessing of the ice. So a complex ice species on top of the dust. Once it is hit by a UV photon, it can be turned into refractory organic material. And then the chemistry stops. So once it's refractory organic, it's taken out of the chemical equation, it's chemically inert. Can't go back, can't go on. We decided that a complex ice has either 3 or more carbon atoms or 2 carbon atoms and 1 heavy atom, because, well, decisions need to be made. And we estimated the rate from lab experiments where interstellar ice analogs were irradiated with UV radiation. So here are some results. I show here the number of monolayers of ice, solid lines, and refractory material and dashed lines for the oxygen-rich and the carbon-rich outflow. Now, different colors correspond to different outflow densities. Let's start first with the oxygen-rich outflow because it's quite simple. There's a lot of ice being formed here, but there's not a lot of carbon-rich feedstock material for refractory organic material. So the coverage is very low. The refractory coverage in the higher density outflows reaches only 0.001% of the surface. So that's a negligible coverage. For the carbon-rich outflow, the situation is different because there's plenty of carbon floating around. And we can reach a coverage of 10% here. And what's interesting is that also these low density outflows have quite a significant refractory coverage. So the purple and brown lines. And that's exactly because of the lower density. This means that there's less shielding against interstellar UV radiation. And in fact, what we see is that as soon as a complex ice is formed is on the dust, it gets photoprocessed into refractory material. So that's what we see here. In order to estimate or just to quantify the refractory organic contribution of AGB outflows to the ISM, we calculated a model for an observational grid of carbon-rich AGB stars. So here we have the grid, mass loss rates, thanks, and the outflow velocity. And the color scale corresponds to the refractory coverage of the model. We did it for 3 sets of parent species, so the ones that we used before. Then one's based on observations as compiled by Agundes, and then here again the observational set with maximum amount of carbon. And we find that on average, carbon-rich dust has a refractory coverage of 3 to 9%. So it doesn't enter the ISM bare, but at the same time, it's not significant enough to influence the ISM. But if we look at these higher mass loss rate outflows, the coverage can range between 8 to 22%. So looking at certain specific outflows in more detail will be interesting to see what type of refractory organic material and how much of it they produce. So again, to our overview/conclusion slide, photoprocessing is a viable reaction in AGB outflows. Oxygen-rich dust is only negligibly covered. Carbon-rich dust, well, there's some coverage, but not enough to influence the ISM. But in order to better understand the refractory contribution or just to model the contribution of specific carbon-rich stars, we need a better grasp on chemical things such as binding energies, but we also again need to better understand the grain size distribution and the drift velocities throughout the outflow. And in this set of interconnected questions, I'd like to end my talk and thank you for your attention.
Thank you, Marie. So again, if anyone has any questions, please put your hand up. Sophia Ramsted, go ahead.
Thank you, Marie. Very nice talk. I learned a lot. So in the beginning, you seem to hint, or at least say maybe straight out, that you can constrain the drift velocity, or that your models are very sensitive to the drift velocity. So can you, and maybe you had it in one of your slides and I just missed it, but do you have an idea of what, within what range it should be?
Well, I'll just go back to my slide here. So that's this slide. These different shades of blue correspond to different drift velocities. So the depletion depends on the drift velocity. So perhaps we can constrain the depletion from the drift velocity from the depletion level, but well, it's all interconnected. What I would really need as an input is the drift velocity, because as you can see, it can have quite an effect, and then again sputtering takes over. But yeah, drift velocity is now more of a free parameter. I always vary it because it can have an influence, but yeah, this is something where observations and theory, well, my models would need to iterate, and yeah, I'm looking forward to do so. Let's put it that way. I'm also interested in knowing the drift velocity.
Yeah, thank you.
Thanks, Sophia. Thanks, Marie. Does anyone else have a question? Okay, remember you can always ask more questions in the Slack if you think of them later. So thank you very much, Marie, for that nice talk. Next up, we have Michele Trabucchi, who will be talking about advancements in the modeling and interpretation of long period variables.
Yes, thank you. So can you hear me and see my screen?
Yes, we can.
Okay, very good. So good morning, everybody, or good afternoon, good evening, depending on where you are. And I'd like to thank the organizers for this opportunity they gave me to present my work today. This will be about a study that I published earlier this year on the nonlinear modeling of long period variables, and a work made between these two institutes, so the University of Geneva, where I'm currently employed under a Swiss National Science Foundation grant for studying long period variables in the Gaia era, and the University of Padua, where I've been working up until a couple of years ago, and where this work started under funding from the ERC project Starkey, PI'd by Paola Marito. Now, long period variables are evolved luminous red giant stars with low to intermediate mass progenitors that undergo stellar pulsation and exhibit variability with periods of orders of hundreds of days and optical amplitudes of a magnitude or more. These are example light years from a few observational programs, all the lasers and the Gaia mission, and actually are for a specific subtype of long period variables that are the Myras, possibly the most famous and interesting ones that are representative of the very final stages of HB evolution. But long period variables are a wide and heterogeneous family, so they also include semi-regular variables that are on the average with smaller amplitude, shorter periods, lesser degree of regularity in their light years, indicative of multi-periodicity, and are not necessarily HB stars. They might be less evolved red giant branch stars or even red supergiants. The importance of pulsation in the evolution and death of these stars and in the shaping the chemistry of the stellar mediate was already stated in previous talks, and I'm sure it will be remarked throughout this conference. But pulsation is also important for a number of other applications. It can be used for studying the structure and dynamics of stellar interiors, for inferring global stellar parameters from variability observations. It can be used for constraining stellar models. And of course, the stellar variability is a well-known powerful tool for measuring stellar distances and possibly inferring ages. And LPVs can be used to these aims, although of course they are a little bit tricky on observational grounds, since they span a wide range of amplitudes and periods. Gathering the appropriate data set for systematically studying these objects requires the right combination of photometric sensitivity and long-time observational baselines. An example of satisfying these requirements is again the other program, quite exceptional in its kind. Here you see the period amplitude diagram of LPVs in the larger Magellanic Cloud according to the EvoLved data release. As you can see, they span more than 3 orders of magnitudes in amplitude and a similar range in period. And to add upon this complexity, these stars are often multi-periodic. They follow several different period luminosity relations, so they are a bit challenging observationally. But as EvoLved got there, a number of other modern surveys are working towards this kind of data collection. For instance, this map, sky map, shows the data from the Gaia data release 2 catalog of long period variable candidates that, although limited to objects with a G-band amplitude larger than 0.2 mag, meaning 2 orders of magnitude larger than EvoLvd's limiting amplitude, it's already rivaling with EvoLvd by number of sources. Of course, because of the full sky coverage compared with the relatively small patches covered by EvoLvd. In about a year, there will be another guided release, increasing this data set. Another example is the Vera Rubin Observatory being built in Chile that will carry out the LSST survey dedicated to time domain astronomy. So owing to this kind of surveys, the opportunity to exploit the potential of LPVs is really becoming concrete. So theory has to keep up with the pace, and the fundamental test for theory would be to be able to reproduce the period luminosity diagram of LPVs. For example, once again here in the Large Magellanic Cloud from EvoLvd data matched with 2-mass near-infrared photometry. On the right panel, you see a theoretical counterpart of the diagram that was obtained by using a synthetic stellar population model of AGB and RGB stars in the LMC, computed with a trilegal code, combined with a grid of linear pulsation models that I worked on during my PhD. Now, as you can see, the blue, green, and orange sequences of your tone pulsation period match relatively well the observations. The same is not true for the fundamental node, which period is systematically overestimated with respect to the period luminosity sequence C, where we found the minor variables that are the most promising in terms, for instance, of distance indicators. This issue affects a number of other prescriptions that are found in literature and commonly used. In all of these cases, the fundamental node period is overestimated. All of these studies were based on linear models. That's why we turn to nonlinear modeling. Now, nonlinear models are nothing especially new. Even for long period variables that are tricky to describe because of the important role of convection in their interiors, these stars, these codes able to perform this kind of analysis have been out for at least a few decades already. They have kept being improved and upgraded. But the novelty from our study is simply that we addressed a systematic analysis that was never really performed before as a function of varying global stellar parameters for the AGB phase and in direct comparison with linear predictions. So motivated by the hope of mitigating the discrepancy between theory and observation, we addressed this study with the aim of providing the community with novel, easy to use prescription to compute accurate fundamental node pulsation periods for stellar models representative of MIRAS and related long period variables. The procedure we follow is relatively straightforward. Everything starts with a hydrostatic equilibrium straightly symmetric envelope model for a representative of an AGB star defined by input parameters, mass, luminosity, and composition. We perform linear stability analysis to compute reference linear periods. And then we use the nonlinear code to solve the time-dependent equation of hydrodynamics to obtain a nonlinear synthetic time series. Basically, a description of the motion of the envelope layers as a function of time and a variation of their thermodynamical properties. Then we perform a Fourier analysis to compute the period of the dominant pulsation node, and we iterate in luminosity to get a sequence of such models with fixed mass and composition, and then we change the other parameters, especially mass and the mixing length parameter, in order to variate on the surface temperature, and we obtain a grid of nonlinear pulsation models that, for the time being, is limited to in chemical composition to oxygen-rich, roughly Magellanic clouds-like metallicity. This is an example of the results for a sequence of 1.6 solar masses models showing the dependence of the period of the dominant mode as a function of the stellar radius of the model. You can see symbols represent the new nonlinear results, while the line represents reference linear periods. And if we focus on the regime dominated by overtone pulsation, we see that the results from linear and nonlinear treatment are essentially the same, which is good because we already know that linear overtone periods match the observations. Actually, this is true also for the fundamental mode, as long as the radius is not too large. In that case, things change. This change seems to be triggered by the increase of amplitude, in this case in terms of surface displacement. In other words, this is defined as the distance traveled by the optical surface from maximum compression to maximum expansion. When this value becomes comparable with roughly 50% of the average stellar radius, that's when the nonlinear periods deviate from the linear trend and settle to smaller values that is exactly in the direction we want to move towards to recover agreement with observations. In order to understand this, we need to look at the interior model. So if we select a low luminosity model dominated by overtone pulsation, and we look at the motion of selected mass layers as a function of time, we see that most of them in the interior are fixed constant, while this gray shaded area near the surface is actually a densely packed pattern of oscillations. So this means that in this case, oscillation is limited to the surface region and with small amplitude. But if the fundamental mode is dominant, the oscillation becomes higher in amplitude and interests also the inner layers. When radius becomes large, we see that even the deeper layers pulsate to a relatively large amplitude, to the point that after some relaxation time, the location of the average location of these layers moves inwards with respect to the static model. In other words, the pulsating layers contract and become denser with respect to the static model. And by a naive application of the period mean density relation, this explains why the period is shorter. This is nothing especially new. It was already found out by Yari and Tuckman in 1996. But they only had a few models at their disposal, so they could not connect this trend with global stellar parameters that we can now do. So we model these resulting period radius relation from nonlinear models as a power law broken into points. First, a bending point where the nonlinear period deviates from the linear trend, that is the gray lines in the background, and then a saturation point after which the period becomes actually independent of the radius. By best fit, as usual, we obtain a nonlinear period mass radius relation that can be used on one side, for instance, to constrain to infer masses and radii from variability observations, and on the other side to predict fundamental mode pulsation periods for stellar models, evolutionary tracks, or for instance, synthetic stellar population models. And in that case, that's what we did to compare with the observed period luminosity diagram. So this is the result, and you can immediately see that with respect to the predictions from our linear models from 2 years ago, now the predictions from nonlinear models match the observed location and slope of the period luminosity relation of Meyer variables in the LMC, the white line here. Now, this is, of course, limited to oxygen-rich LPVs because of the current limitations of the grid in terms of chemical composition. But it works rather well both in the LMC and in the SMC. For the details of the simulations, I invite you to read Giada Pastorelli's paper and also to look at the poster during the poster session. Just quickly, if we apply this to the evolutionary tracks, we see the evolutionary path of these tracks in the PL diagram, which finally explains the right edge of the PL sequence of Myras due to the new shape of the period radius relation. The final few words about chemical composition. As I said, the grid is now limited to oxygen-rich Magellanic Cloud-like composition, but we did a few tests for carbon-rich and solar-like metallicity, and preliminary results suggest that A higher metal content might induce shorter periods at a given radius band, not at the same luminosity. This is different. Possibly a similar effect is present in terms of amplitudes, but further investigation is required for this. So I will conclude leaving you with a summary of this talk. I want just to remark that this is really the first accurate prescription for fundamental node pulsation periods that's around, so please use it. And a few next steps that we plan to do is to extend the grid in chemical composition and investigate multiperiodicity, especially the transition between different dominant nodes as a function of global stellar parameters. Finally, we hope to be able soon to predict synthetic light curves so that we will be able to predict both periods and amplitudes of variability in different photometric bands. So this concludes my talk. Thank you very much.
Thank you very much. We already have a raised hand from Boris. Go ahead and ask your question.
Hello, can you hear me?
Yes, I can hear you.
Thank you, very interesting talk. I have a quite basic question probably. Do you consider the pulsation which you consider, are these solar-like acoustic oscillations, or is this kappa mechanism?
So no, they're not stochastic oscillation. They are self-excited pulsations. The actual driving mechanism is not especially clear, but is basically some sort of kappa mechanism with involvement of convection.
Okay, thank you. I have some other questions, but I think it will be better to discuss them in Slack probably.
Then I'll see you on Slack.
Thank you.
If anyone else has any questions, feel free to raise your hand. But if not, Boris, maybe you can ask another question.
No, I'm not ready by now. Sorry.
So Theo has a question. Go ahead.
Hi. So it's very interesting talk, thanks. And but I think my question is probably not going to be super relevant because a lot of it went over my head a little bit because not my area of study. But so how much would you say that this is a prediction, and how much are you actually fitting these observations there? Is it that you're introducing, in your approach, you're somehow giving more freedom to this pulsation model so that you can fit what is observed, or is it really a different approach in which the outcome is unique and it happens to match the observations?
Okay, so
that makes sense.
I realize that I seemed a little speedy through this explanation. Basically, we are computing two different grids of models. One is a linear grid, so basically we compute the natural frequency of resonance for the stellar structure. This is the linear approach. The nonlinear is different. We start from the static model and let it evolve in time. So the pulsation naturally develops, the motion of the layers naturally develops. And this allows for feedback from pulsation onto the structure that becomes different from the equilibrium, the static structure. So also the frequencies of oscillation become different. Our approach in implementing these results into the simulation is basically, well, the simulation is a mock catalog, is a list of simulated sources with given masses and radii and luminosity in different photometric band. So we use this relation to compute the period for each source. Then we display them. We simply compare the period luminosity diagram. So it's just a different kind of modeling.
But when you have this table with the parameters that you pass through now, do these parameters affect how these curves look, or if you vary them, or?
Well, yes. So if I mean, we varied, as I shown, the mass, and you can think as luminosity and radius as a sort of similar things. So the period increases with luminosity as it increases with radius. There are also differences with mass. So I can show you a couple of extra slides. So basically, these data points here are the best fitting parameters for each data point is a different mass. We kept fixed mass and fitted as a function of radius. And then we fitted the best fit parameter as a function of mass. So this hides a little bit the difference in terms of mass, but you can see here in this, it's a little small, but you see here, each different color is a different period radius relation for a different value of mass. So mass and radius do affect a lot the resulting period, of course. There are some effects due to temperature that we change with the mixed length parameters. There's a smaller, and we did not investigate yet other global stellar parameters, namely the chemical composition. We only know that there might be effects based on this exploratory experiment.
Okay, thanks.
You're welcome.
Thanks, Chair and Michele. We have run out of time for questions. Unfortunately, Lane, you'll have to ask your question in the Slack.
Okay.
So that's in the hashtag #day1 channel. So thank you to all of our speakers today. Some great talks there.